All right. All right. Make sure you grab a calculator because you're going to need it for today's stuff. Okay.
Big old chair, workbook. Come on, spine,
All right. So today we're talking about z-scores. How do we find them mathematically? How do we do a process to find them? Also interpreting them. What does it mean? Z-scores are associated with percentiles as we use them to calculate percentiles and stuff. Now, what is a z-score? A z-score is a standardized score. Okay, it's standardizing the values in a data set is what z-scores are basically. They're a standardized, and I'm going to write that down here. They're a standardized score. They are a standardized score of each data value. And so we use them. The reason why we use them is so we can compare. We use them so we can compare data values. Now that sounds kind of vague, but it goes back to the standpoint. How many of you taken the ACT? All right, I took the ACT too. It took me like almost 40 years ago. Okay, so would it? And as we look at it, you know what your score is. I know what my score was. I was a one and done. I took it once and I was done. I didn't want to take it again because I hate taking standardized tests. I took the SAT once and then I was done. And we look at our score, and I had somewhere probably like a 22 or a 23 is what I got for my score. And then you know what your score is right now. Hey, did you get bigger, better than I did, or did you do the same, or did you do worse than I did? And then we say, okay, numerically, okay, you may have gotten better than what I had, or you may have been worse. The challenge is we technically aren't supposed to compare my value to your value because the tests were two totally different tests. Besides just the day of the test, the makeup is totally different. You guys do reading, English, math, and science. We did 4 subjects: history, science, math, and English. So a score on my version of the ACT shouldn't be compared to a score for your version of the ACT because we weren't tested on the same exact material. It wasn't the same concept, the same curriculum or makeup. I had history, you didn't have history. And so what we do is we do this standardizing. We use these z-score thing, and we standardize my score, we standardize your score, and then we can compare who did better. And that's what we end up doing when we look at why do we use z-scores. It's so that we know we can't compare apples to oranges. So what we do is we standardize them. Now I can compare them. Whoever had the higher z-score did better. Whoever has the lower z-score didn't do as well. Okay? So that's the whole purpose, is when we're trying to compare 2 different sets of data, like the different versions of the ACT, or maybe your ACT score and your SAT score. We know they're compiled by 2 different methods. One's out of 36 points, the other one's out of 106 or 1,600. And so how do you know which one did you do better on when they don't have the same grading scale? And so that's what we do, is we standardize it. Then we can say, okay, this is the test I did better on, once I make it to a standardized score. And that's why we end up using z-scores, not just in education, but in other things when we're trying to compare things that are measured differently. If I standardize it, now I can make a comparison which was the better. Okay, which one was worse. All right. Z-scores can range from being positive numbers to negative numbers. All right, there's no limitation to how big or small they are. You could have a z-score of 0. That is a possibility, and we're going to talk about that as we do things. So that it just gives you a little idea of why we do it, so we can compare apples to apples and oranges to oranges. So here are the formulas. They're pretty much identical. A z-score represents the distance that a data value is away from the mean. It's how far away a data value is away from a team's in terms of standard deviations. So when we get this z-score for a particular data value and we get it to be like 1.67 or something, then it's roughly 1.67 standard deviations above the mean. Because as we look at things, positive z-scores mean you are better than the mean. Negative z-scores means you are below the mean. The reason why we can get a z-score of 0 is because you scored exactly the mean. Because if I knew the mean was 50 and I scored a 50, well, what's 50 minus 50? 0. Okay, and on the top of our fractions here, we're basically take each, the plain old x's in each cases here. That's basically your, if we want to write it, this is basically the actual amount minus the mean divided by the standard deviation. And that's the same thing for both things. It just depends on if you're talking about a sample z-score or a population z-score. Usually as we're asked to do multiple problems, like I'm going to have you do here in our notes here, we usually use the z as an indicator and then use a subscript to indicate, well, this z value represents the z-score for this actual number. So I'll write some of those things with like a subscript to go through there. A z-score is unitless, has no units on it, okay? When we look at our z-scores, this little statement here, I'm gonna talk about it being mainly when we have a when all data values in a table / distribution have been converted to z-scores. Oh, I have it written down there. I typed it in there. Daggone it. So that's the statement right here. My bad. So I was thinking that was the next little note there. I apologize. That whole thing right there. When a set of data values or a distribution, because we're going to use that terminology later, when those things are all converted to z-scores, which means they've been standardized, and so we need to make sure we pay attention to that word standardized, because that automatically lets me know for certain calculations in the future, I can use the mean as 0 and the standard deviation as 1. Okay? If they say that, this distribution of data has been standardized, I know the mean 0 and the standard deviation is 1. Okay? So that's a tip here we want to make sure we remember. So I have an example. I have several examples. We're going to walk through this. And so we'll get a lot of practice. Right here, they say determine whether the Boston Red Sox or Los Angeles Dodgers have a relative better run production season. The Red Sox scored 876 runs in playing the American League, whereas the mean number of runs scored was 731.2 and a standard deviation of 72.6 runs. The Dodgers scored 804 runs in playing the National League, where the mean number was 710.8 and the standard deviation was 60.2. Now, it's both baseball. Okay, now they made a point to pick a team in both leagues. Okay, and for those that don't have any idea why they did both leagues, those that know, can you share with us why? Why did they pick somebody from the American, somebody from the National, as opposed to taking two teams from the National League or two teams from the American League? Why do you think they did that? Is there a difference?
They play completely different teams.
They play different teams. Okay, when you look on average, they do cross division, cross league playing. Now, I know I have baseball players in here. I do follow Major League Baseball. Kind of separated a little bit. I just watch more towards the playoff time. I know when I grew up and somewhere into the early 2000s, I don't know if it's changed in the last 5 years, biggest difference between the National League and the American League was that the National League, the pitcher batted. Okay? And said, whereas the American League always had a DH. Now recently they did some switching. Okay, are they both batting now, or are they both DHing? Both hitting?
No,
Okay.
I think both have a DH now.
Yeah, both have DH.
Both have a DH now. Okay. So that's where when you look at maybe this problem was created, it was based on when I was growing up and until recently. Within the last 5 years, it changed to where, hey, if the pitcher is pitching and the pitcher typically is not that good of a batter, then the run total for a National League team will be a lot less because most of the time when a pitcher came at the bat, majority of the time, they got struck out or they grounded out. Now, some of them got on base, some of them hit home runs and did stuff, but it wasn't like a high average of that occurring. And so that's why the run production, when you have in the American League 9 true batters that are consistently batting every day, 4 at-bats at a game or whatever it is, as opposed to a pitcher that may bat once every 4 games or every 5 games, or a relief pitcher that comes in once every 10 games because they're a middle relief or something. Their batting averages are not going to be that high, and therefore their run total for that team may not happen to be as great while those guys are in. So that's why they picked these 2 things, one from each league, because their leagues aren't technically the same. Okay, their makeup wasn't beforehand. So now, in order to see which team was better, we need to standardize that. We need to standardize stuff. Okay, so with that in mind, let's go over here. We're going to say the Red Sox, and we're looking for the Z-score for the Red Sox. So I'm just going to do a Z-score for Red Sox. That season, 876 runs. That's the X. The mean for the American League was 731.2. Over the standard deviation for that American League was 72.6. And then now we're just going to break out and go to the calculator. So now in the calculator, you can type it in as a big fraction or just be careful. I'm just going to subtract the 2 numbers on top. I'm going to get 144.8. And then I'm going to divide that by 72.6. And that gives me a standard deviation of 1.9945. We want to take it out a bunch of decimals. 4 decimals is good because sometimes the first 2 may be a tie. So we take it out to kind of 4 decimals as we do things. Now, the Z-score for the Dodgers. They scored 804 runs. The average for the National League, was 710. And the standard deviation for the National League was 60.2. So then we go through 804 minus 710.8. That gives me 93.2 divided by 60.2. So divided by 60.2. And that gives me 1.5481. So now we get to decide who had a better season in run production. Since the Red Sox had a higher Z-score than the Dodgers, they had a better run production season. Again, since now that we converted to a standardized score, we converted to a standardized score by using each individual value and then their mean associated with that, in this case, league, and dividing by the standard deviation of that league. And then now that we can see that, hey, 1.99 is bigger than 1.54, so the Red Sox had a better season based off of run production. Don't know how it finished that year. I don't know which year they're talking about. I don't know if both teams made it to the World Series that year. We don't know what year they're talking about. But if we're just analyzing from the standpoint of run production, the Red Sox had a better season because they had a bigger Z-score. Okay? There's a big old bug. Now, birth weights. Here's another one we get to practice. Babies are born after a gestation period of 32 to 35 weeks have a mean birth weight of 2,600 grams and a standard deviation of 660. Babies born after a gestation period of 40 weeks have a mean weight of 3,500 grams and a standard deviation of 470 grams. Suppose a 34-week gestation period baby weighs 2,400 grams and a 40-week gestation baby weighs 3,300 pounds, or 3,300 grams, sorry, that would be a real big baby. What is the Z-score for the 34-week? What would be the Z-score for the 40-week? And which baby weighs less relative to the gestation period? Okay, so that one's going to be a little bit different. So we're still going to start it the same way, but when we go to compare it, bless you, we're going to... So we're first going to go Z-score for the 34 week. So I'm going to do Z sub 34. So when we see these subscripts on some of the variables we're using in this lesson, that just is a way to identify which one we're talking about. Instead of having like two Z's on a piece of paper, we have the Z for this one and a Z for that one, and it's more of a labeling purpose. So for the 34 week, 2,400 grams was the actual. They said the mean for a 32 to 35 was 26, so minus 2,600, and a standard deviation of 660. That'll give me a negative 200 over 660. Now I'm going to go to the calculator. Again, it's okay to have a negative Z-score. That means that we were below. That means that we were below the mean. And so that gives me a negative 0.3030. The Z-score for a 40-week old baby. They said in that example, a 40-week baby weighed 3,300 grams. So 3,300 minus the mean for that gestation period was 3,500 divided by a standard deviation of 470. So that would still be a negative 200 on top divided by 470. So 200 divided by 470 gives me a negative 0.4255. So now our interpretation of the question, we got the Z-score for both. Now we have to say which baby weighs less than relative to the gestation period. So in this case, I would say the interpretation is who's got a smaller Z-score. So in that case, this would be who has a smaller. And as we look at this, what's smaller? Negative 0.3 or negative 0.42? It's actually backwards in the negative world. Okay? Negative world is backwards. And then that's why I paused. I didn't want to go straight into it. Common thinking is, hey, it's a smaller number. Yeah, 0.3 and 0.4. But it's on the other side. Okay? When it's saying less, it's weighing less than, means it's actually further away from the mean and the negative side. So in this case, it would be, this one would be this the Z-score of, for the 40-week-old, that one would be actually less. Oops, that'd be less because bigger negative. Bless you. And that's the tricky part on some of these things, is just the way they ask to phrase the question. Okay? So both of these cases, they were below the mean. We can tell that by the way how we set up the top of the fraction. Technically the 34-week-old baby was closer to the mean because as we look at its Z-score, it was bigger, so it was closer. A smaller negative means you're bigger and stuff in the negative world. All right, men versus women. You can work ahead of me as you're going through. I'm hoping you're getting a hang of what we're doing here. The average 20 to 29-year-old male is 69.6 inches tall, and with a standard deviation of 3 inches, while the average 20 to 29 woman is 64 inches tall. So again, if you're not sure what that is, 69 inches is how much? 5 foot what? Yeah, that's 5 feet 9. Average is 5 foot 9 for a man. Okay. So female, they're saying on average is 5 foot 4. So now, who is relatively taller, a 75-inch man or a 70-inch woman? So we got the man. So we want to find the Z-score for the man, and we want to find the Z-score for the woman. All right, 75-inch man. So 75 minus 69.6 over 3. That gives me 5.4 on the top, divided by 3. It should be 1.8. And then for the woman here, a 70-inch woman minus 64.1, standard deviation of 3.8. So who is relatively taller when you standardize them? This gentleman, the man who is 75 inches tall, is relatively taller than the 70-inch woman because his Z-score is larger. Now, the next one I'll give you a chance to get ahead of me and do. It's always one of those things we hear about in sports with athletes. Who is the better when they start comparing across generations. I don't know about you guys. I don't think you guys are on Facebook as much as I am. You guys are more the TikTok and the Instagram and that kind of stuff more than I am. But I know I always see these little feeds on Facebook saying, "Hey, who's better, Michael Jordan or LeBron James?" And I always see these little things coming out there about those things, and everybody has their opinion. I've seen things out there comparing. Well, Jordan was 6-0 in the finals. LeBron's 4-8 or something like that. Jordan hasn't played as many years, and he had all those accomplishments in fewer years by a bunch, and so forth. So but now it's like, okay, but they also play two different positions, and so if we're going to decide, we need to standardize some values to decide that. So like in this example here, Mookie Betts. Anybody know where Mookie Betts went to high school or went to college?
Didn't he live here?
Yeah, he was in Nashville. I want to say, I don't know if he was Antioch, that area for high school.
I think he went to Overton.
Overton?
Yeah,
So kind of that area? And then for college, did he go MTSU or did he go Vandy? Look it up. Let's see what it is. I thought he went local for college too. I didn't think he was like far away. David Price went to Vandy. Right?
Yeah, he went to John Robertson High School and he went to Tennessee or UTK.
You went UTK?
Yeah.
Okay. I thought he was closer. Okay, so with that in mind, and Mookie's been in the, doing well the last several years a bunch. So Ted Williams, a famous old baseball player. Let's compare who had a better season in that one season. So let me give you a chance when you do the Z-score for Ty Cobb's 1941 season and then Mookie Betts' 2018 season. And then we can decide, okay, based on those seasons, who had a better season. Because a lot of times we just look at the batting average and say, well, 406 is better, But again, there was a difference between those time periods. right, I think I got an extra 0. If you look at where oh, never mind. No, I didn't. My eyes are off. That's the standard deviation. My apologies. I was thinking. I was looking at that 0.0328 as being the mean. I was like, there ain't no way that mean average was that. Standard deviation. That makes sense. All right, so with that in mind, again, yes, common sense says, hey, a 406 batting average is better than a 346 batting average. However, did they play the same number of games? No. Okay. Yeah, they were both in the American League, but again, they didn't play the same number of games and so forth. So, we want to make sure we standardize it. Now we have the things. Now we have numerical data after standardized saying, "Hey, Ted Williams had a better season than compared to Mookie Betts because his standardized score is higher." So so relative to his peers, Williams had a better season. Now, we can use not only z-scores for the purposes of comparing two data values together once it's been standardized. We also are associating z-scores with percentiles, where a certain z-score represents what percent of the data is below it, and that's where there's a connection to it. So we're going to talk about percentiles later on in some lessons. We'll talk about how I can take a percentile, convert it to a z-score, and then figure out, how that happens, or how do I take a z-score and figure out what percent of the data is below it or above it. That's in a later lesson that we can end up doing in a future chapter. So where do we hear percentiles? When have you guys heard percentiles? When have you heard that used? Yes, ma'am. Height and weight percent. Whenever we went to the doctors growing up and stuff, especially you all that are in, the track here doing your clinicals and stuff, that's where it's a little bit more in your vocabulary now. Also, where else can we see percentiles besides that? Talked an example earlier about the ACT. Don't you usually get a percentile score? You scored in this percentile in this category, whatever. Okay, so that's usually where we see percentiles. We either see it associated medically in some form or fashion, especially when kids are growing and young and stuff. They're saying, hey, you're in the 40th percentile for height and the 20th percentile for weight and so forth is when we usually see, especially as parents. Then as we get into the educational field with the standardized testing, whether it's end-of-course exams or ACT, it comes out saying, hey, based on your score, you're in this percentile. And we talk about, well, if I'm in the 70th percentile, that means I scored better than 70% of my peers in that category or on that test. Now, that also meant 30% scored better than me. Okay, we always refer to it as what's less than is what we usually refer to. So that's where we talk about the little p. Here's my little symbols here. So if I was going to talk about in like this first example, it talks about the 15th percentile. I'm going to use that symbolic notation to write what we're doing. So they asked us to explain the meaning of the following percentile, the advanced data for vital and health statistics, the 15th percentile of head circumferences for males 3 to 5 months of age is 41 centimeters. So again, as we look at symbolically, if you see on like, we would say that's like P sub 15 is what we'd say, and that would be known that that's the 15th percentiles that represents. We would somehow explain it, meaning that 15% of the males ages 3 to 5 months, have a head circumference less than 41 centimeters. And so, and again, that's what they're just asking us to do in these first couple examples, is just say, what does that statement mean in just generic talking? So 15% of the males aged 3 to 5 months have a head circumference less than 41 centimeters. On the next example, again, you can get ahead of me in writing it, P sub 90. What does that mean? Just explaining that 90% of the 2-year-old females have a waist circumference less than 52.7 centimeters. So the 52.7 centimeters is the waist circumference, and we know based on this study, the statistics, 90% of the 2-year-old girls have a waist circumference of that amount and less. Okay? So only a 10% have a waist circumference bigger than that. Percentiles are always what's less than. Now, here's where you got to be careful, because they always like to throw little curveball phrase questions when we see things. Sometimes we'll have to find the score associated with the top 10th percentile. If I'm in the top 10 percentile, then that means 90% is below me. Okay? So we have to remember that if they use the phrasing top 10 or top 15, like we do for graduating for honors and so forth, like when we do graduation for high school, we have the top 15% of the class. Okay? And so the top 15% means that, hey, 85% of your peers have a GPA less than you are. Okay? So we have to be careful when we're asked to find eventually specific values associated with a top 15 or a top 10. We have to actually convert it over to the opposite version to go through the math to do it. Okay? If they ask you to explain something like that, where it said the top 10%, we would say, hey, 10%, the 10% of the, in this case, girls have a waistline more than 52.7 or greater than 52.7. All right. Percentiles are closely related to quartiles. Quartiles, again, divide our data sets into 4 quadrants. Quartile 1, 2, 3, and 4. Each of the quartiles represent 25% of the data, no matter if the thing is symmetrical or not. Once we have our data set and we find our quartiles, each quartile contains 25% of the data, is what it has. We label the first quartile as Q1. The second quartile is Q2. We usually refer to that as the median. The median is where the second quartile is the kind of where it occurs. And then the transition from the second quartile to the third, we have the third quartile. There's 75% of the data is to the left of it. And so here's just a little thing to keep in mind, that the first quartile is associated, Q1 is associated with the 25th percentile. Q3 is associated with the 75th percentile. The median, or Q2, is associated with the 50th percentile. Now, as we were doing stuff in our calculators yesterday with the measures of variance, even measures of centers last week, and we were using technology to find our information, it did give us what Q1 was, what Q2 is, what Q3 is. Okay? And that's part of some of our lesson today. We find, to find, do I have that down there? No. To find Q1, median, Q3, use 1var stats. We can do it by hand, but again, as we noticed yesterday, we get a lot of data sets, so we might as well just type it in, let technology find it for us. When we're doing it by hand, when we're finding Q1, we actually don't include the median if there's an odd number terms. So you take all the way up to the median, stop, don't use that number, then you find the halfway mark of that first half, and that's Q1. And then to find Q3 in an odd number of terms, you would go to the median, stop, find the middle of the last half of the data, and that's Q3. So it gets really crazy. So in each of the different programs out there statistically, whether it's the TI-84, it's the Excel, it's the Minitab, and those different applets, they all have it set up just a smidge different. Okay, so that's why sometimes if you use multiple technology devices, you may have a little bit difference between the quartiles and so forth. It's because they have the algorithm set up a little bit different. We experimented that with one of my classes before with Excel and the TI-84, and there was a difference between what it was. So just know that kind of going into it. So in this one here, we're going to go through, type this data in, and we're going to figure out what the quartiles are. So what's Q1, what's Q2, what's Q3. Remember, Q2 is also is phrased as the median. Okay, we usually don't refer to it that much as Q2, but it is. So as I swap over here, let's get our calculator going. Boom, 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 boom. TI-84. There we go. There we go. So, again, you can plug, sugar beets. There we go. All right, so as we start going into stat, I'm assuming you guys know where you're going from here. So into stat, then we start typing in. Be careful with happy fingers. All right, so I think I got all my stuff in there correctly. I got 3 of 18. Yeah, I got 18 numbers in, so I'm hoping I didn't have happy fingers. I go stat, go over to calculate, 1var stat. All my stuff is in L1. There we go. And then I'm going to scroll down. Notice we saw the mean. We saw the standard deviations. We don't need those. My Q1 is 735. The median is 1805. And the Q3 was 4668. And again, in our next lesson in 3.5, we talk about the 5-number summary, which is basically the minimum through the maximum. Those last 5 data values are what we call the 5-number summary. And that's in the next lesson that we'll get into here in a minute. So the quartiles, Q1, the median, and Q3 are part of the 5-number summary. So that's all they asked us to do there. The interquartile range is the range of the middle 50%, so that's the box. So when we think about a box and whisker, because we did box and whisker in the a box plot in the earlier chapter, so that's the box. The IQR is basically what's the box, and it's the range of the middle 50% of the data. To find the IQR, all you do is take Q3 minus Q1. So for our example up above, with that sample there, the IQR for the above problem would have been 4668 minus 735. And so 4668, bless you there, 735. And we get 3993. So as an interpretation, we would say, so the middle 50% of the data has a range of $3,933. Now, why do we use the IQR? Okay, again, it's a range, but it's the range of the middle set of the data. There's some benefits to use the IQR because if we think about the full range, we could have some outliers. And the outliers could really distort what's taking place with our data set and overinflate, what our range is. Whereas if I do the IQR, it's around the middle 50%, so it gives me a better idea about the dispersion of the middle 50% of the data. And so that's why, especially when we have, and we'll talk about this in a little bit, when we have data that is skewed, we actually use the IQR as a way to talk about the measure of spread or the measure of variation. If it is symmetric, then we use the standard deviation. Okay, and we have those in places in our notes over the last couple lessons, and I'm sure I have it again in here in a little bit. So, here it is. So as I get rid of the calculator, interpreting the IQR, again, I just did that example, the range of the middle 50% of the data. What is it? So we usually want to use the context of the problem. So whatever that last one was, collision coverage. So the insurers, so there'd be the middle 50% of the middle 50% of the data for coverage claims had a range of $3,933 is what we'd kind of say on that one. Again, as I just talked about, if our shape of our distribution is symmetric, when we look at the measure of center, we use the mean. When we talk about the spread or dispersion, we use standard deviation when it's symmetric. So when it's approximately bell-shaped. If it is skewed left or right, for the measure of center, we use the median. And we use the IQR for the measure of dispersion. Very rarely do we use the range for doing a measure of dispersion. Okay? The only time we would is if they don't give us all the data values and all we have is like we just have the minimum and maximum. Then we're forced to kind of use the range in that context to talk about the spread. But if we're given all the data values, that means we could find the IQR by finding Q3 and Q1. And so it's preferable that we use that when we're given all the data values. So when asked to describe data, you need to make sure you use that as your template there. So make sure you memorize that as we do things, not only for homework, but also for testing. Make sure you have that idea. Here's the longer portion of this section. Checking for a data set for outliers. Okay? Just because a number looks further away from the rest of the data, we just can't say it's an outlier. We have to prove it mathematically in this class. And then that's what we have here is we have an outlier rule. It's basically called the 1.5 times IQR rule is what it's called. And we use this rule to determine does a set of data have any outliers? Okay? Prior to now, when you were growing up, teachers just asked, hey, which data value looks the furthest away from the rest of the data? And then like, okay, that's the outlier. Now as we're growing up, we're getting more into the statistical aspect, there is a set calculation we do. So what we go through and process-wise, I have a couple little notes there. Go ahead and take your time reading those on your iPads. As we look at checking for outliers, we use the quartiles. So we first have to determine what Q1 and Q3 are, find the IQR, then I determine what's called fences, which is kind of like my upper bound and my lower bound. What's my cutoff as an upper fence where anything equal to that number and greater is an upper bound, kind of a outlier, and then my lower fence is anything equal to that number and smaller than that fence is an outlier in the smaller direction. So to find the lower fence, we take that answer from the 1.5 times IQR and subtract it from Q1. That gives us our lower fence value. To find the upper fence value, whatever 1.5 times the IQR added to Q3 gives us our upper fence. So with that, then we get to decide if something's inside or outside those things. We can cut it out. So here is a problem that we get to do, and they want us to figure out is the z-score corresponding to obtained by this. Compute the z-score, interpret this rate. Okay, now, so they want us to find the z-score for that. So that's one part. Then they ask us to determine if there's any outliers in our data set. So let's quickly find the z-score for this 36.3. So let's get that data typed into L1, do a 1var stat, get our mean and get our standard deviation so we can figure out what that z-score is. So again, I'm going to do this on a hand calculator just because I can type faster there and don't have to worry about junk. All right, so all right, so I did that, and let's go in there. All right, let me know if anybody got this as well, because that way I know I didn't have happy fingers. I got a mean of 38.775. Anybody else get that too? Sweet. All right. Again, sometimes when we go so fast, we make mistakes. The big thing here is as you do this process, this is a sample, so let's use S sub x because that makes a difference as we look at our z-scores if we want to compare. I'm going to use the S sub x, 3.41648. That should be plenty. So as I look at the z-score, I have 36.3 minus 38.775 over 3.416488. So clear that screen. And I'm going to go ahead and do that. 36.3 minus 38.775. That gives me a negative 2.475 over that long decimal. And then I can go through and say, all right, what's that divided by 3.416488? And I get a z-score of approximately negative 0.7244. All right, so there's our z-score. Was that below the mean or above the mean? Is that Z-score above the mean or below the mean? Yeah, it's below. Why? It's negative. All right, it's a negative value, so that means that it was below the mean. Okay, that amount, that mileage per gallon was below the mean. All right, so we answered the first one. That, and again, we have to interpret it. We would say that the individual who obtained a 36.3 miles per gallon was negative, was 0.7244 standard deviations below the mean, is what we would go through and describe as a sentence. What are the quartiles? Again, I'm just going to go back out, get a 1 var stat. It probably would have been more economical just to go ahead and write it down when we first did it. So as I look at my 1 var stats, Q1 is equal to 36.85. My Q3 is 41. Again, using the min, the max, and the median are my 5-number summary, but I don't need them for this part. So my IQR is 41 minus 36.85. So clear screen, 41 minus 36.85 gives me 4.15. So that's my IQR. Now as I go to figure out outliers, I have to find my fences. I got my lower fence, which is technically Q1 minus 1.5 times the IQR. So now I'm going to go ahead off to the side here and say, okay, what is 1.5 times the IQR? Let me get that amount. So take my 4.15 times 1.5, and I get 6.225. So I need to take 36.85, subtract 6.225, and that tells me what my lower fence is. So 36.85 minus 6.225 gives me a lower fence of 30.625. Now I got to find my upper fence. On my upper fence, we take the Q3, so 41. It's Q3 plus the 1.5 times IQR. So that would be 41 plus 6.225, which would be 47.225. And then now I look to see, do I have any numbers in my table smaller than 30.625 or bigger than 47.225? So that one's okay, that one's okay, that one's okay, for 47, okay, we're good. No, that's okay. No, nope, 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 nope. Hey, nobody. So there are no outliers in that data set. Okay, there's no outliers in that data set because we did not have an example of something being below 30.625 unless I made it goofy.
I think the last one was 7.5.
Was I checking off too fast? You're right, sweetheart. I was. I'm sorry. I was getting too far ahead of myself. You're exactly right. There is one outlier. Let's make that correction. There is one outlier. It happens to be 47.5. That was my one outlier. Okay? And again, it's all my AP stats books and my honor stats book, they teach that if you're equal to the fence and greater or equal to the fence and less, you're an outlier. I didn't notice anything when I went through the textbook with this publisher, them making any note different than that. Okay, so that should be okay to use that same logic on homework. If you have a data value on the fence, it's an outlier. Okay, so as you're working on homework, let me know. If one of the data values is on the fence and it doesn't do that, let me know, because all my other textbook curriculum I use, they say fence and the other directions, those are outliers. Okay, the fence is included as an outlier. So, and that's the challenge when you go from writers and authors from publisher to publisher, they all have a little different interpretation. And that's where we just got to adjust as students and so forth. So the next thing here, again, they want us to find what is the wait time for 40 visitors at the Disney dinosaur ride. Hey, we can get some real data. We can get some of the cheerleaders and the dance team to kind of send us back wait times as a thing, and we can get like live data of what is it, what's happening. But here, let's go through real quickly, do this one. Determine and interpret the quartiles. Check the data set for outliers. Again, it's a long process, but using technology makes it go really quick is what ends up happening. So I'm going to go ahead and put that into my L1. And stats, get an L1. I'll ask you to double check in a minute. Yes, you got to put 0 in there. If you didn't have the weight, what does that usually mean you had? Either no line or a what? If you go to Disney and some of the resorts and you don't have to wait to get on a ride, there's either no line or you have a fast pass? Whew, that's a lot of numbers. All right. Oh, I missed somebody. I'm on line 40. I missed somebody. Sugar beets. Oh, I missed 4. That's all I missed. Order doesn't matter, so it's okay. I can do that. Now, stat. All right, here we go. So my Q1. I'm going to go ahead and write down the 5-number summary. Again, 5-number summary is the min, Q1, Q2, which is the median. That's in our next little lesson we're going to spend about 5 minutes on because it's like super fast. Q3, and then the max. All right, so there are my quartiles. I know what Q1, 2, 3 are. And then now if I want to find out if there's any outliers. IQR is 18.5 minus 5, which is 13.5. And then I got to do 1.5 times the IQR, which would be 1.5 times 13.5. So 1.5 times 13.5 gives me 20.25. And then now for the lower fence, we have to do Q1 minus 20.25. So 5 minus 20.25 would be a negative 15.5 or 15.25. And then, and then on the other side, the upper fence, we would do Q3 plus the 20.25. So Q3 was 18.5 plus 20.25, which would be 38.75. So we know there are no outliers below because we can't go back in time. So there's none below. Now we just got to look at, 38.75. I see a 44, a 52, a 39. Did I miss anybody by going too quick? I think I got the 3 of them on that one. All right, so there are 3 outliers on the upper side, 3 outliers on the upper bound. They happen to be 39, 44, and 52. Again, using technology makes this go a heck of a lot quicker, okay, as opposed to doing it by hand like we did back in middle school, trying to do some of those kind of things, okay? So use the technology. I would say try to stick with using the online TI-84 if you don't have one. That way it just, you're familiar with it as we're doing testing. I do have some extra problems here. I know you can do this first one here, converting all those ones to get their z-scores. I put a couple of these other word problems in here as extension problems in case they give us a z-score and ask us to find for something different. Because technically, when you look at our formula, z equals x minus x bar over s sub x. And it doesn't matter if you're using mu and sigma on there as well. We have technically 4 variables in that problem. If I know 3 of the 4, I can find the 4th one. And that's what one of the applications is we've been practicing always solving for the z. As we look at this one here, they actually tell us what the z-score is. They tell us that the z is equal to negative 1.8. They tell us the standard deviation, that'd be s sub x, is equal to 2.5. And the mean x bar is equal to 39.2. They asked us to figure out what was the x value. We're missing x. We're missing the actual x value that gave us a z-score of a negative 1.8. So in this case, we're going to do some back solving. Negative 1.8 equals x minus the mean divided by the standard deviation. Again, the highest level of mathematics to do a stats course technically is Algebra 2. That's all you need. In some cases, it's Algebra 1. But it's really Algebra 2 is all you need for math skills to do something like this. First thing is we multiply both sides by 2.5. So 2.5 times a negative 1.8 gives me a negative 4.5 equals x minus 39.2. I then add the 39.2 over, and then when I add 39.2 to the previous thing, I get that x is equal to 34.7. So that was the actual PSI of the tire that gave us a z-score of a negative 1.8. And this is where I'll always say, stop, does it make sense? Our z-score was negative, which means that it was below the mean. Is my answer below the mean as a number numerically? Is it smaller? Okay, so that'll be a quick check. Did you do something wrong in the inverse operations? If you have a negative z-score, your answer should be smaller. If you're looking for the actual, should be smaller than the mean. Okay. All right, again, there's just more practice problems just like those. Let's scooch over to 3.5 just to talk about some of the things here. The 5-number summary, again, I worked it on that previous problem. It's the minimum, the min, the quartile 1, median, quartile 3, and the max. We'll push that out real quick. It doesn't deserve a second day just because we've been using that feature so much. Thanks for the heads up there. Good thing I didn't make you like handwrite it like the old days. Just make you just handwrite all this stuff. That was the hardest part about college is when they don't give you templates and they make you handwrite everything that's on the board or the screen. And you're just writing the whole time and like sometimes can't process what they're saying at the same time. So hopefully you don't get too many of those professors in your future. Did you get it? Okay, sweet. You never know with the internet. So the 5-number summary, again, comes from the 1var stats. It comes from the 1var stats statistically. Notice that the mean and the standard deviation are not part of it. Okay? It's made up of those 5 things. And these 5 things help us draw the box plots. That's one of the purposes of why do we use it. It helps us to draw the box plots so that when we have to do parallel box plots and compare 2 sets of data, then we can put them on the same grid and then compare who had a greater spread, dispersion, so forth, who had a higher median. I already have that in there. That I don't know why I got that part in there again. All right, there we go. There. Oh, how do you draw a box? We really don't need the fences. You can use the fences. That's why I got it in there. So when you're drawing a box plot, basically, we have typically our minimum. Q1 is the left side of the box. Q2 or the median is the middle of the box. Q3 is the right-hand side of the box. And then typically our last number is our max. Now, the only time when it's not is when our max or min could be an outlier. Okay, and that's where in here it talks about that. If you have something that is an outlier, we use an asterisk to indicate it somewhere. So we draw the fences to kind of give us an idea, and then when I find if something's an outlier, I just put an asterisk somewhere, and I don't connect the whisker to it. Okay, I denote outliers as an asterisk, because otherwise if I draw the line to the min and the max is an outlier or the min is an outlier, then I don't know where outliers are. So here we have associating the relationship between a histogram and our box plots is what we have here. On the list, starting from left to right, when my histogram is skewed to the right, so it slopes down to the right. Notice there's a lot of more data on the left-hand side. There's a greater frequency of the data on the left compared to what's on the right. When we look at our box plot, we should see a bigger tail with the right-hand whisker going from Q3 out to the max, out that way. We also should see, in this case, the skinnier, notice how we're kind of skinny in this area here. The skinnier a whisker is and a box, part of a box is, that means there's more data in it, is what that means. The wider a box is and the longer a whisker is, that means it's more spread out. There's more variance in that portion of the stuff. Okay, and so paying attention to the widths of the whiskers and the boxes can dictate, hey, which way am I skewed, right or left? Okay, it's easy to tell when it's a histogram or it's a dot plot. Box plot's a little different, okay? And so when you pay attention to how wide the portions are and then go from there. A symmetrical box plot, the boxes look about the same width, the whiskers are the same lengths, is what they are. And then when we look at a skewed left distribution, it's the opposite. So longer whisker to the left, wider box on the left from Q1 to the median, and then a really smaller Q2 to Q3, and then a shorter whisker on the side. Again, it's telling me that there's more data on the right-hand side. That's why it's a lot smaller, okay? So here's where we just got to be careful a little bit. Identifying the shape of distributions from a box plot or from a histogram is subjective in some cases. Identifying the shape of a distribution from a graph, make sure you support why. So support your opinion when you're saying, hey, it's skewed right. Why? Well, there's more data on the left-hand side. The first quartile and the second, between the first quartile and the second quartile, they're smaller in width, which means there's greater frequency of data in those sections compared to the wider sections of the Q2 to Q3 and from Q3 to Q4. So here they want us to go through and practice drawing them. We can actually, what was the last one we did? What was the last one we have in our calculator? Didn't we have a, do we have a set of data in our we have a set of data in our table, right? So on the previous lesson that we just did, I'm going to do a one var stat and grab the min max and that stuff on it so I don't have to retype in. So going back to the previous problem on the last lesson, because that's a heck of a lot of data to type in. So we had a minimum of 0, a Q1 of 5, a median of 8.5. We had a Q3 of 18.5. The max was 52. But we did decide in that problem there were 3 outliers. Wasn't it 39, 44, and 52? Were those the 3 outliers from that last problem we did on the previous lesson? So as I go to draw my box plot for that last lesson, got to find some nice little scale. So 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. All right. So my minimum was 2. Q1 was Q1. So there's my little whisker. The median was 8.5. So that's somewhere about right here. I'm going to put that for my median. Q3 was 18.5, which was right about here. That's Q3. So I'm going to go ahead and draw my box here. And then now this is where we got to be careful. What was the upper fence? Was it 38 point something? I'm trying to think. I try to memorize numbers, but 38.75. So as I look at, okay, my upper fence was 38.75. So then at 39, I'd put an asterisk. At 44, I'd put an asterisk. And at 52, I'd put an asterisk. So we got asterisk, asterisk, asterisk. And then I would just kind of draw my whisker up until the fence is what I would do there. But I would stop short of that first outlier is what I would do. So these numbers right here are my outliers. I stopped the fence just short of that. I don't have to worry about the left fence because it was negative. We didn't have anything that was negative time. And then you always label any type of graph, and this would be our wait time at the Disney, what was it, dinosaur? A dinosaur ride? Dinosaur ride. Is that the Aladar ride? It's been too long since I've been to Disney. And the last time I was in Disney was 2008 and stuff, so. Any questions? We use the 5-number summary to help us draw the box plots. Use the fences as a cutoff for the whiskers. Make sure your outliers are denoted with asterisks. Okay. Now we can get on the TI calculator, we can get it to draw us a box plot. We're able to do that. So if you look at the screen of my screen, and I'm not gonna do I can do a problem. No, I didn't type it in there. But let me. If you go into second stat plot, and we go to turn on our stat plot, as I arrow down to the type, the box and whisker one that I'm flashing right now, where it's got the 2 dots on it, that's the one where it'll tell it to do outliers, where it'll calculate the fences, and if you see 2 dots outside the whiskers or dots outside the whiskers, you know those are outliers in the box plot. So that's the one that you would use for it to determine the outliers for you. If you use the next box plot, that's going to automatically connect outliers to everything else. We don't want it to do that. Okay, so if you have an idea and you want to check, hey, did I draw it right? Did I find my outliers correctly? That's a nice way to check it in the TI-84.